Here is a photo of Ron Graham. He was a world-class mathematician. I had the pleasure of knowing Ron while he was alive. He has been called the mathematical showman. Besides being a mathematician, he was an expert trampolinist and juggler, as you see here. In this video, I'll tell you about one of Ron's first results, appearing in his PhD thesis. His result is about fractions, specifically unit fractions. You remember unit fractions, right? They are fractions like 1/2, 1/3, 1/4, and so on. They have a 1 on top. We'll also allow 1/1. Besides Ron Graham, you know who else loved unit fractions? The ancient Egyptians. They had special symbols for unit fractions. Here are hieroglyphs for 4 unit fractions. Can you guess what the first hieroglyph means? It's 1/3. The mouth symbol on top means reciprocal, so it's the reciprocal of 3, namely 1/3. How about the second hieroglyph? Yes, it's 1/4. The last 2 hieroglyphs are harder to guess. They are 1/10 and 1/100. The ancient Egyptians loved unit fractions. They wanted to express every fraction as a sum of unit fractions. For instance, here's a document called the Rind Papyrus. It's nearly 4,000 years old. The beginning of the papyrus shows the so-called 2/n table. It's a guide to expressing fractions of the form 2 over an odd number as a sum of different unit fractions. For example, can you write 2/3 as a sum of different unit fractions? The papyrus says 1/2 plus 1/6. It would be easier to write 1/3 plus 1/3, but the Egyptians insisted on different unit fractions for their method of doing arithmetic. Next, can you write 2/5 with different unit fractions? The papyrus gives 1/3 plus 1/15. How about 2/7? The papyrus says 1/4 plus 1/28. The 2/n table in the papyrus continued through 2/101. Notice that the last sum has 4 unit fractions. A single number can be expressed as a sum of unit fractions in many ways. For instance, let's attempt to express 1 itself as a sum of unit fractions. What's the simplest way to write 1 with unit fractions? The simplest way is 1/1. What's the next simplest way to write 1 as a sum of different unit fractions? I suggest 1/2 plus 1/3 plus 1/6, which works because 1/3 plus 1/6 is 1/2. Can you think of some other ways? Here are 5 more sums. Are there infinitely many ways to break down 1 into a sum of different unit fractions? Yes. Some of these expressions are straightforward, while others are more intricate. To determine how complicated a particular sum is, let's introduce a measure of complexity. We're going to look at the bottoms, the denominators of each unit fraction, and add them up. Let's use the same 7 examples from the last slide. What's the denominator sum of the first example? Its denominator sum is 1. How about the second example? Its denominators are 2, 3, and 6, so the denominator sum is 11. How about the third example? Its denominator sum is 24. And we can keep going with the remaining examples. Next is 30, then 31, then 32. The final example here is 37. There are infinitely many ways to express 1 with different unit fractions. What denominator sums will we encounter along the way? Can we identify precisely which numbers can serve as denominator sums? Let's give a name to these intriguing numbers. We'll say that a number n is an Egyptian number if there are different unit fractions that add up to 1 whose denominator sum is n. Let's see some examples. Here are the first 7 numbers in the Egyptian club. For instance, y is 1 Egyptian. Right, because of 1/1. And y is 11 Egyptian. Yes, because of 1/2 plus 1/3 plus 1/6, which has a denominator sum of 11. And we can keep going with the remaining 5 examples. The smallest Egyptian numbers are 1, 11, 24, 30, 31, 32, and 37. Next, let's look at the first few non-Egyptian numbers. The number 2 is not Egyptian. There's no combination of unit fractions adding up to 1, with a denominator sum of 2. How about 3? 3 is not Egyptian either. How about 4? 4 might seem promising with 1/2 plus 1/2, but remember, no repeating unit fractions are allowed, so 4 is not Egyptian. Let's uncover more examples of Egyptian and non-Egyptian numbers. We're going to classify the numbers from 1 to 99 where the colors tell a tale: green for Egyptian and red for non-Egyptian. At first, the Egyptian numbers are rare. Do you think that pattern will continue? At the start, the majority leans towards non-Egyptian, yet as we go further, the balance shifts. Toward the end of our list, most numbers are Egyptian. Take 77, for instance. It is a non-Egyptian outlier in a sea of green. Could it be that 77 is the largest non-Egyptian number? Yes. Every whole number larger than 77 is an Egyptian number. This surprising theorem is due to Ron Graham. I've shown here the top of his paper. Let's plunge into the proof of Graham's 77 theorem. Here is a table from Graham's paper. It shows that the numbers from 78 to 101 are Egyptian. For instance, look at the 78 at the top left. It's followed by a list of 6 numbers: 2, 6, 8, 10, 12, and 40. What do those numbers mean? They are the denominators to show that 78 is Egyptian. Those 6 numbers themselves add up to 78, and when you form the 6 unit fractions with those denominators, namely 1/2, 1/6, and so on, they add up to 1. So 78 is Egyptian. In the same way, this table shows that all the numbers from 78 to 101 are Egyptian. Graham actually needed more starting numbers for his proof. Here is the second page of his table. You can barely read it here, but it shows that the numbers from 102 to 258 are Egyptian. Graham actually needed a third page. Here is the final part of Graham's table. Altogether, he showed that the numbers from 78 through 333 are Egyptian. This table is an excellent start, but to prove the Egyptian nature of all large numbers, we need some clever reasoning. What will be our plan? We will begin with a known Egyptian number and use its property to construct a larger Egyptian number. For instance, we know that 91 is Egyptian. According to Graham's table, the 7 unit fractions here add up to 1, and their denominator sum is 91. How can we use this equation to show that a bigger number is Egyptian? Do you see a way to get bigger denominators? Let's try a trick. Let's divide each side by 2. On the left side, each denominator doubles, resulting in a denominator sum that has doubled from 91 to 182. That's the good news. The bad news is that the right side is 1/2 instead of 1. That's not what we're after. Remember, we want to express 1 itself as a sum of unit fractions. So how do we convert that pesky 1/2 into the desired 1? Let's add 1/2 to both sides. Great! The right side is 1, and the left side remains a sum of different unit fractions. What about the denominator sum? Starting at 91, then doubling to 182, and finally adding 2 more brings us to 184. In other words, 184 is an Egyptian number, thanks to this double plus 2 rule. The only hitch is that double plus 2 will give us only even numbers. How do we generate odd numbers? We'll need another rule. Let's revisit our process starting with 91. Again, we divide both sides by 2. Is there a way to express 1/2 using an odd denominator? Sure. We can represent 1/2 as 1/3 plus 1/6. Let's give that a shot. We added 1/3 plus 1/6 to both sides. Does that give us a new Egyptian number? No. We encounter a repeated 1/6. Remember, we have to use different unit fractions. Unfortunately, this approach hits a roadblock. Let's explore another avenue in our quest for Egyptian numbers. Once again, Let's begin with the equation showing that 91 is Egyptian. After dividing by 2, we are faced with the task of adding 1/2 or its equivalent to each side. Our previous attempts ran into obstacles, so how do we express 1/2 as a sum of unit fractions this time? Enter Ron Graham's ingenious move to generate odd numbers. He represented 1/2 as a sum of 4 unit fractions: 1/3 plus 1/7 plus 1 over 78 plus 1 over 91. We now have a bunch of different unit fractions that add up to 1. How much does the new part contribute to the denominator sum? It contributes 179. Altogether, we doubled the denominator sum and added 179. The new denominator sum here is 361, an odd number. We managed to avoid repeating the same unit fraction in this case. How can we be sure that this rule won't lead to repetitions in general? Recall that initially we doubled denominators, so they were all even. The lone even denominator in the new part is 78, so the only potential repeat is 78, and to avoid it, we must ensure that we don't have 39 as a denominator in the first equation. Can we always stay clear of a denominator of 39? To confirm, let's revisit Graham's table of starting Egyptian numbers. Recall this table from Ron Graham earlier, showing that the numbers from 78 to 101 are Egyptian. Our goal is to sidestep the denominator 39, and I'm pleased to report it's nowhere to be found in this table. Graham had 2 other pages of the table showing that the numbers from 78 through 333 are Egyptian. Not once does he use the denominator 39. Fantastic news! This means that we won't encounter repeated unit fractions as we construct larger Egyptian numbers. Okay, we've cracked the code to generate both even and odd Egyptian numbers. Let's bring these 2 methods together. We know that 78, 79, and so forth through 333 are Egyptian numbers, with no need for 1 over 39. What will the double plus 2 rule give us? Applying the double plus 2 rule to the starting sequence, we obtain the even numbers 158, 160, and onwards through 668. What about the double plus 179 rule? Employing the double plus 179 rule to the starting sequence, we usher in the odd numbers 335, 337, and the like, extending all the way to 845. Thanks to not using 1 over 39, we sidestep any unwelcome repeats of unit fractions. What's next? Let's weave together the even and odd numbers. Starting from 78 through 333, we continue with 334 from the even list, followed by 335 from the odd list, then 336, 337, 338, 339, and so forth, all the way to 669. We've proven that the numbers from 78 to 669 are Egyptian. Furthermore, no 1 over 39 was introduced along the way. Great progress! We've expanded our list of Egyptian numbers. Our upper limit has surged from 333 to 669, more than doubling. In fact, it doubled plus 3 more. What's our next move? Let's replay the entire process, revealing more Egyptian numbers. Okay, we now know that the numbers from 78 through 669 are Egyptian. Enter the double plus 2 rule, and the Egyptian charm extends to the even numbers 158, 160, and onwards through 1340. Following suit, the double plus 179 rule reaches the odd numbers 335, 337, and the like, up to 1517. Again, let's blend these even and odd numbers together. Starting from 78 through 669, we proceed to 670, then 60 to 71, and so on, extending through 1341. Hooray! We've proven that the numbers from 78 through 1341 are Egyptian. Another extension of our list, more than doubling the top number. What's next? Let's keep the momentum rolling. We started by knowing that 78 through 333 were Egyptian. Our trip continued upward to 669. Then we pushed the boundary to 1341. In one more leap, we can stretch the list to 2685. And so on. The pattern persists. We keep revealing more and more numbers as Egyptian. If we continue in this manner, we'll eventually reach every whole number beyond 77. So, to conclude, we finally proved Ron Graham's 77 theorem. Every whole number greater than 77 is an Egyptian number. In the video description, I've provided a link to Graham's paper, where he proves this theorem and more. Thanks for watching.